In the Fraunhofer far-field regime, the light source, the slit, and the observation screen are all effectively at infinite distance from each other, or are made to behave as if they are by using a lens. This means that the wave fronts arriving at the slit are planar, and the diffracted waves emerging from each point of the slit are also planar, just tilted by a small angle theta. A single slit geometry is simply a long, narrow, rectangular opening of width, of the dimension measured perpendicular to the direction of propagation cut in an opaque screen. The slit is much longer than it is wide, so we can treat the problem as one-dimensional. The field varies only across the width x negative a over 2 less than or equal to x less than or equal to a over 2. In practical labs, a laser beam is collimated, passes through the slit, and a lens of focal length f focuses the far field pattern onto a screen placed at the focal plane. Because the lens maps angles theta to positions y equals f times theta on the screen, measuring a pattern on the screen is equivalent to measuring the angular distribution of the diffracted light. Explanation: to find the intensity, we add the contributions of all the infinitesimal wavelets that originate from each point x inside the slit, Huygens Fresnel principle. Each wavelet has the same amplitude A0, but a phase that depends on the extra path length to the observation point at angle theta. The path difference between the wavelet at position x and the one at the center of the slit is x sine theta. The corresponding phase difference is k x sine theta, where k equals 2 pi over lambda, the wave number. E of theta equals the integral from negative a over 2 to a over 2 of a naught e to the I k x sine theta dx. Carrying out the integrals, E of theta equals a naught times sine of open parenthesis k a sine theta over 2 close parenthesis divided by open parenthesis k a sine theta over 2 close parenthesis times a. Define the dimensionless parameter beta equals pi a sine theta over lambda, which is also k a sine theta over 2. E of theta equals a naught a times sine beta over beta. The intensity is proportional to the square of the field magnitude. I of theta equals I naught times open parenthesis sine beta over beta close parenthesis squared. Where I naught equals absolute value of a naught squared is the peak intensity observed on the axis. Theta equals 0, i.e., beta equals 0. The limit of sine beta over beta approaches 1 is taken. This is the classic single-slit Fraunhofer pattern, a bright central lobe flanked by a series of weaker side lobes. The minima of the intensity occur whenever the numerator sine beta becomes 0, while beta is not equal to 0. Sine beta equals 0 implies beta equals n times pi, where n equals plus or minus 1, plus or minus 2, and so on. Substituting back for beta gives the angular positions of the dark fringes. Pi a sine theta n divided by lambda equals n pi, which gives sine theta n equals n lambda divided by a. For small angles, which is usually the case, sine theta is approximately equal to theta in radians, so theta n is approximately n lambda divided by a. The spacing between adjacent minima is therefore delta theta equals lambda divided by a. The maxima are not exactly halfway between minima, because the function sine beta over beta squared does not have zeros of its derivative at the simple points beta equals n plus 1/2 pi. The first secondary maxima occur at solutions of tangent beta equals beta. Tangent beta equals beta, which give beta approximately 1.43 pi, 2.46 pi, 3.47 pi, and so on. Their intensities are only about 4.5% of the central maximum, which is why in many textbooks only the central lobe is emphasized. Y sub n plus 1 minus y sub n equals f delta theta equals f lambda divided by a. This linear fringe spacing is the practical quantity measured in experiments. The central maximum extends from the first minimum on one side, n equals -1, to the first minimum on the other side, n equals +1. Its angular width is therefore delta theta central equals 2 theta 1 approximately 2 lambda over a. In linear terms on the focal plane of a lens, the width is w equals 2 f lambda over a. Thus, a narrower slit, smaller a, gives a wider central bright band, while a wider slit produces a narrower central band. The dependence on wavelength is the same. Longer wavelengths produce a broader central maximum. This reciprocal relationship, width proportional to lambda over a, is a hallmark of diffraction and reflects the wave nature of light. The tighter the confinement in space, small a, the greater the spread in direction, large angular width. Explanation: if the wavelength is increased while the slit width is kept fixed, every beta value becomes larger for a given angle, so the sine squared envelope contracts less quickly. Quantitatively, the minima move outward, because sine theta n equals n lambda over. For example, doubling lambda doubles the angle of the first minimum, so the central lobe becomes twice as wide. Conversely, making the slit wider, increasing a shrinks the angular spread. The same n gives a smaller sine theta n. If a is made much larger than lambda, the pattern approaches the geometric optics limit. The central maximum becomes very narrow, and side lobes become extremely weak, almost invisible. Qualitatively, small and narrow slit, broad pattern, few fringes visible, bright central spot. Large a wide slit, narrow pattern, many closely spaced fringes. Central spot looks like a thin line. Short wavelength, blue light, tighter pattern, more closely spaced minima. Long wavelength, red light, broader pattern, minima farther apart. These trends are useful in applications such as spectrometers, where a grating acts like many slits, and optical metrology, measuring tiny dimensions by analyzing diffraction spreads. Suppose a laser of wavelength lambda equals 632.8 nanometers, he shines on an unknown single slit. Using a lens of focal length f equals 200 millimeters, we record the distance between the central maximum and the first dark fringe on the screen y sub 1 equals 5.0 millimeters. The relationship between the linear distance and the angle is y equals f times tangent theta approximately f theta for small angles. So theta sub 1 approximately y sub 1 divided by f equals 5.0 millimeters divided by 200 millimeters equals 0.025 radians. From the minima condition sine theta sub 1 equals lambda divided by a, and using the small angle approximation sine theta sub 1 approximately theta sub 1, we solve for the slit width. A equals lambda divided by theta sub 1 equals 632.8 times 10 to the minus 9 meters divided by 0.025 approximately 2.53 times 10 to the minus 5 meters equals 25.3 micrometers. Thus the slit is about 25 micrometers wide. The same procedure can be used with higher order minima n equals 2, 3, and so on to improve accuracy. The result should be consistent within experimental error. Case steps for students. Step 1. Measure the distance y sub n on the screen. Step 2. Convert to angle theta sub n approximately y sub n divided by f. Step 3. Apply a equals n lambda divided by sine theta sub n, or a equals n lambda divided by theta sub n for small angles. Step 4. Average over several orders to reduce random errors. Mathematically, the Fraunhofer diffraction pattern of any aperture is the squared magnitude of the Fourier transform of the aperture function a of x. For a single slit, the aperture function is a rectangular window. A of x equals 1 when the absolute value of x is less than or equal to a over 2, and 0 when the absolute value of x is greater than a over 2. Its Fourier transform using spatial frequency nu equals sine theta over lambda is f of a of nu equals the integral from negative a over 2 to a over 2 of e to the minus I2 pi nu x dx, which equals a times sine of pi a nu divided by pi a nu. Identifying beta equals pi a nu, which equals pi a sine theta over lambda, reproduces the sine beta over beta factor derived via Huygens principle. Hence the diffraction pattern is literally the power spectrum of the slit's transmission function. The Fourier transform view clarifies why changing the slit width inversely scales the angular width of the pattern. A narrow rectangle in real space, small a, has a wide sinc function in frequency space. A wide rectangle has a narrow sinc. This duality is a general property of Fourier pairs and underlies many imaging systems, such as the relationship between the pupil function of a microscope and its point spread function. In practice, engineers use this concept to design optical filters, compute the modulation transfer function of lenses, and analyze antenna radiation patterns, where the aperture is the antenna's physical size. Multiple choice, choose 1. 1. In Fraunhofer diffraction from a single slit, The first dark fringe occurs at an angle theta that satisfies A sine theta equals lambda, B sine theta equals 2 lambda, C sine theta equals lambda over 2, D sine theta equals 3 lambda. Answer A. 2. If the wavelength is halved while the slit width is kept constant, the angular width of the central maximum will A is double, B halve, C remain unchanged, D become 4 times larger. Answer B. Short answer. 3. Write the expression for the intensity distribution of a single slit Fraunhofer pattern and define the parameter beta. I of theta equals I sub 0 times open parenthesis open bracket sine beta over beta close parenthesis squared, where beta equals pi sine theta over lambda. Answer: I of theta equals I sub 0 times open parenthesis open bracket sine beta over beta close parenthesis squared, where beta equals pi sine theta over lambda. 4. Explain in one sentence why a narrower slit produces a broader diffraction pattern. A narrower slit confines the wave in space, which by the Fourier transform uncertainty principle produces a wider spread in angular spatial frequency space. Answer: a narrower slit confines the wave in space, which by the Fourier transform uncertainty principle produces a wider spread in angular spatial frequency space. Numerical problems. 5. A green laser lambda equals 532 nanometers shines on a slit of unknown width. Using a lens of focal length f equals 150 millimeters. The distance from the central maximum to the second dark fringe on the screen is measured as y sub 2 equals 8.0 millimeters. Calculate the slit width. A solution sketch. Dash angle for second minimum theta sub 2, approximately y sub 2 divided by f equals 8.0, divided by 150 equals 0.0533 radians. Dash for the second minimum, n equals 2. A equals n lambda over sine theta sub 2, approximately 2 times 532 times 10 to the minus 9 meters divided by 0.0533, approximately 2.0 times 10 to the minus 5 meters equals 20 micrometers. Answer: approximately 20 micrometers.